So we have seen the exact difference between what is z-score for sample data and z-score for sampling distributions. Okay, so now it's time to demonstrate the usage of z-score to do statistical significance test between two variables, or to understand the statistical significance of relationship between two variables, or to do the feature selection using statistical significance test between two variables, or to select one feature with respect to the target variable using z-test. So that's what we're gonna demonstrate in this example, in this slide. So we will begin with the first step, importing libraries. So whatever the libraries are required, that can be imported in the first step. So NumPy for numerical computations, pandas for data manipulation, scikit-learn linear regression for performing linear regression, and scipy.stats for statistical functions, and matplotlib for plotting the scatter plots or whatever you require. And that's what is going to be our first step. So the step one is importing libraries. So import pandas as pd, import numpy as np. That's it. That's what is our first step. Let's get back to the slide again one more time. Then a second step for us is to setting up the data. Setting up the data is nothing but here loading the data, and after that assigning the respective columns to the x variable and y. It's like referencing the respective column to the respective variable reference, such as which is, it's like labeling which is dependent variable, which is independent variable. So that's why these are called supervised machine learning, because you are giving the labels, you are labeling which is dependent variable, which is independent variable. So here, so that's what we are going to do. We are going to say one column as x, which is independent variable, another column which will take it as a y, which we call it as a target variable. And that's what we will be doing now. Let's do it. So loading and setting up the data, and here, so let's say data is equal to pandas dot read csv, and read csv. Then let's call the data here. It's just a minute. Yep. Salary dot csv, and let's execute. If you just want to see, you can just print the data, and this is some, you can do some exploratory data analysis regarding the data set. Then what you see here is you got the two columns basically. So one is years experience, other one is salary. So what we do, let's take salary as our dependent variable, or you can call it as a target variable. On the other side, years experience, you see here years experience, which is independent. So the salary target variable, or is a target variable, and years experience is a feature for us. So target variable is dependent on years experience. Okay, that's what we are gonna do now. So let me take y. So y is equal to, that's what is our target variable. Y is equal to data of salary Okay, and x is equal to data of years experience. Let me take this one. Yeah, let's try to see what is y, which is our target variable. Sorry, y, which is our target variable. Here it is. This is the, okay, yep, salary. That's our target variable, you can see, and the salary is dependent on x. And what is x for us? X for us is years of experience, and you can see that. So obviously what I'm trying to say is the salary of the employee is dependent on years of experience, and that's how we have taken. And this is the data setting. Next, so now it's all done, all set. It's time to perform simple linear regression. So simple linear regression will be done in two steps. Performing it will be done in two steps. In first step, you have to instantiate the linear regression class object, and in second step you have to call up the method from the instantiated linear regression class object and fit the data into the fit method as an argument. So in this case we will give the x column to the x variable and y column to the y variable. So two arguments it's gonna take, and then it's a positional arguments. The first one you have to give x values, and the second one you have to give the y values. Or by default, in linear regression algorithm also, the target variable has been identified as a small y, and the feature has been identified as a capital X or capital X1, capital X sub 2, capital X sub 3, capital X sub 4. Okay, so this is what we'll be doing now, performing simple linear regression. So just to perform that, we need to import a specific uh, library and a module from the specific library which can do this work. So who can do this for us? Only thing is sklearn. That's what we widely use. So from sklearn, of course you can do with the stat models also, but still we'll go with the sklearn because most of the data scientists use this because it's much easier and intuitive to do that. Okay, from sklearn library linear model package, we will import the linear regression module. We will import linear regression module. So now we can instantiate the linear regression class object. So that's what we will do. So performing linear regression. So let me say model is equal to linear regression. So with this we are calling up the linear regression class, which does mean we are instantiating the linear regression class object, and we are referencing that linear regression class object with the variable name called model. So now I can use all the methods which are available under linear regression class. So one of that method is model, one of that method is fit, and that's what I'm going to do. So model is object, and I'm going to call up the fit method, and the fit method I have to give two arguments. One is capital X and second one is Y. With this we are fitting the data into the algorithm or into the model. So because of that, what is going to happen? So as it is a linear regression equation, this here the pattern in the data set will be captured in the form of linear equation. If you fit with polynomial equation, if you fit the same data into the polynomial regression, equation, then the pattern of the data will be captured in polynomial equation. If you fit it in tree regressors, if you fit it in SVM regressor, super vector regressor, so what you get is a respective, the pattern in the data will be captured in respective mathematical equation. That's what is fitting, or some other way, the fancy way of telling is training. This we call it as a training. Okay. Anyway, with this, what is the output? Output is pretty simple. We'll get an equation which has captured the pattern of the respective data. So how will you tell that? Because the coefficient, with coefficient and intercept is what is going to capture the change of uh, change of x. What amount of change of x causes the change in y? Okay, how much the x influences the y? That's what the coefficient says, and that's what the pattern of the change of data was captured in linear regression as a linear regression equation or linear equation. Okay, so now it's time to extract the coefficients because our fitting the model is ready. Now let's see how it's been fitted. Okay, now if you just want to check exactly what is model, the type of model, and here it is, you see that base is a linear regression. Linear regression, when you say a linear regression base, sklearn library linear model package, from that you got the base dot linear regression. It's a class object, that's clear. And if you want to check it some other way without just asking type, and what you get is this linear regression class again. Okay, it's an object. Okay, so now it's time to see how, what's the pattern of data, what kind of pattern, what pattern this data has in terms of linear regression, because that's what we are interested about. So let me extract the coefficients for that, because unless you extract the coefficients you can't understand. So let's extract the coefficients. So coef, let me call it as a coef is equals to model dot, I have to use coef underscore method, coef underscore method from the model object to get the coefficient of it. Okay, and here is my coefficient. Let me print it, and here let me print coef. And so I got a coefficient of 9,449. That's what my coefficient. Now let me call up intercept also. So intercept is equal to model dot intercept underscore, and let me print the intercept also. So print intercept, and this is my intercept. So with this, my equation is ready. So let me say y is equal to, y is nothing but your years of salary is equal to 9,000 and that's x, capital X, which is nothing but the years of experience, plus 25,000. This is our intercept. So this is what the fitting the model. This is what we call it as the fancy way of saying is training the data or training the algorithm. So this is what happens when you use a fit method from the respective object. What is going to happen is it's going to take the x values, it's going to take y values, and it's going to capture the pattern of data in terms of the mathematical equation that you have provided. If you provide a linear regression, you will get a linear equation like this. And here what we say is this much of, when 1 unit of x changes, y will change 9,449 units. And and this intercept is a constant. uh, it doesn't change every time. Okay, so this is what the pattern it has observed and it has captured, the model has captured in terms of linear regression or linear equation. If you give a polynomial equation, what you get is a polynomial equation. The pattern will be captured in the polynomial equation. If you give SV super vector regressor, you would have gotten pattern. The pattern would have been captured in super vector regressor's equation, and that's what is a training. It's nothing but it's fitting data, or training data is pretty simple, capturing the pattern of the data in terms of the mathematical equation that you have given. Here in this case it's pretty straightforward. One unit change of x causes 9449.96 units of y, and that's what is your fitting the model. Okay, so now it's done. Performing the simple linear regression is done, and extracting the coefficients is also done. So coefficients and intercept obtained from the linear regression models are extracted. So the coefficient is stored in variable coefficient as we have discussed earlier, and representing the slope of the linear regression equation. Now step 5, performing the z-test. So now what we understood is there is a relation, there is a nice relation. We got that, and an equation of a linear equation, but we just want to make sure whether the feature and the relationship between them is statistically significant or not. To understand the statistical significance relationship of the two variables, we should need to go for z-test, because in this case both are continuous variables, both are numerical variables. So we will go with the z-test. Okay, so we'll begin the statistical significance test procedure from now onwards. Whatever we have done so far was modeling. So now it's time for the statistical significance test. So let's begin with null hypothesis. Let's formulate the null hypothesis and then alternate hypothesis. That's where our process starts. So null hypothesis, what it says is there is no significant relationship between years of experience, which is x, and salary, which is our target variable. In other words, the coefficient of the years of experience feature in the regression model is 0. Okay, and obviously the alternative hypothesis is there is a significant relationship between years of experience and salary. So the coefficient of the years of experience feature in the regression model is not equal to 0. Let's formulate the hypothesis first. So we have entered into the step of performing statistical significance test using z test or z statistic or z test. Okay, so now so let's begin with formulating the hypothesis. Formulate hypothesis. Okay, so first null hypothesis, which is h0. Null hypothesis is h0. So here what we say is there is no significant relationship between salary and years of experience. Okay, and So which actually means our sample mean, we'll take it as a sample mean, but basically our coefficient here h0 is, in this case, h0 in this case is coefficient, because that's what is going to decide the relationship between two variables and y and x, because the change of 1 unit change of x causes this amount of change in y, correct? So the coefficient, so we'll take it as a 0. So we will call this, normally in formula we'll call that a sample coefficient. We'll call it as a sample coefficient mean. Okay, and let's take it as a 0. This is for the null hypothesis. On other side, ha, which is equal to we say there is a significant relationship between salary and years of experience, so which also means coefficient is not 0. Obviously, if coefficient is 0, which means there is no significant relation, because y is equals to 0, so there is no connection with the x. So that's our null hypothesis. But on the other side, alternate hypothesis, what we say is there is a significant relationship between them. That means coefficient is not 0, it's something else. Okay, uh, it's some other value, it consists of some other value. Okay, formulating the hypothesis is done. It's time to move ahead. So let's compute a standard deviation. Let's compute the standard deviation first. So what is standard deviation here? Standard deviation would be calculating for the y, because that's what is our target variable. Because what we are doing, we are asking how much of x influences y. So that is the reason we are taking the coefficient as the connecting term, which is the influencing factor. Coefficient is the one which is influencing factor, and then standard deviation of y, the each value of y or each values of the target variable. Okay, so here the sample standard deviation of target variable will be calculated using standard deviation method with the argument. Obviously we have to give the degrees of freedom, that is very important, which applies Basel's correction for an unbiased estimate, and this is how we calculate the sample standard deviation. Let's say it as a sample, don't get confused. Here sample standard deviation is nothing but the target variable standard deviation. So let me take it. Okay, let me calculate that, but before that I have to import the respective items. Okay, for me numpy has been imported, not to worry here. So let me calculate the standard deviation of the target variable. That's what is our immediate target. Calculate standard deviation of target variable. Okay, so let me say n is equals to length of total, what's the length of our variables. Let me print it here, print n, so 30. That's okay, this is what, and to calculate the standard deviation we require n also, that's the reason. So now let me say sample underscore target variable standard deviation is equal to np dot, I'm using standard deviation std method from numpy, and inside I'm gonna give y, because that's where I want to calculate, and degrees of freedom is equal to 1. So this unbiased sample standard deviation, what we get is, so let me print it. Let me say this is coefficient coef coefficient, and this is our intercept. uh, okay, and this is our sample size. Let's take it as a sample size. Here sample size is nothing but your total number of observations or data points that you have. Okay, now let's also print standard deviation. Standard deviation, which can also be called as here sample standard deviation. Okay, and here it is. This is what the standard deviation with the mean in each individual salary is varying this much. Okay, that's fine. So standard deviation also has been calculated. Now it's time to go for the next step. So uh, once you have computed the sample standard deviation, now it's time to calculate the z-score. So to calculate the z-score, obviously this is for the statistical significance test. So that's the reason we will be using a different another formula. So that is a sample mean subtracted sample mean minus population mean divided by standard deviation of the sample divided by square root of n. That's what the formula we're going to use. And so let's calculate the z-score. uh, let's calculate the z-score first, and then just for the z-score we can we have to import one more module from one more library or one more package. Let me do that first. So from scipy import stats. Basically this is this is for the probability, but however I have taken now only, that's not an issue. Okay, let's go back to the work. So z-score, z underscore score is equal to obviously coefficient. Here for me it's sample it's what's my coefficient value. So this is my this is my coefficient value. So that's the reason I'm gonna give just coefficient. Okay, minus what's my population mean I'm considering, or you can call it as a hypothesized coefficient. Let me call this also hypothesized coefficient. Let me say hypothesized hypothesized coefficient. Yeah, hypothesized, because whatever the sample mean, whatever the population that mean that you take is not exactly the population mean. It is the hypothesized mean. We call it as hypothesized mean. You will assume, basically assumption. Here I am assuming that the hypothesized coefficient is 0 because I believe there is no relationship between both. So that's the reason I am checking this. Okay, so divided by standard deviation, which is nothing but what I'm sample target standard deviation. So let me directly take this one and sample target standard deviation, which is divided by np dot, I need to go the square root of sample size, which is n again, which is sample size or total number of observations in our data set. So with that z-score has been calculated. Now it's time to print the z-score. So z-score, yeah, yep. So this is what the z-score we got. It's 1.88, and that too positive. And of course what we are doing is a two-tail z-test. It's not one tail, it's a two tail z test. So that's the reason you have to consider on both sides. 1.88 means on a positive side and negative 1.88 and positive 1.88, because this is two tail test. Anyhow, okay, let's move ahead. So what we are doing is a two tail test, because either we are saying there is no relationship or there is a relationship. We are not specifically talking about whether the relationship is positive relation, that's a coefficient is positive, or whether it is a negative relationship, that's the coefficient is negative. That's what not we are saying. So that's the reason it's a two tail test. Okay, so z score has been calculated. So what's next? The fun activity is ahead. So once the z score has been calculated, now it's time to calculate the probability value or p value. So p value. So the p value is computed using the cumulative distribution function or of the standard normal distribution, or if it is a continuous variable, you can say it as a probability density function pdf or cdf. So here let's take the p value. We'll calculate from the stats module that we have recently imported. So let me go back to the Jupyter notebook. Now let's compute the p value. Okay, p value, p underscore value is equal to stats. Obviously from stats I have to take a norm module from the stat, and there I have to come with the standard distribution, which is sf method, and inside that np dot I want absolute score of z score, because it's a two tail test. I'm not worried about which direction. So, and obviously I have to multiply with two times. It's because it's a two tail test. Sorry, it's two tail test. Okay. So what? Let me print the p value now. P value. Just copy paste. That would be much easier. Here and here too. Yep. And we got 0.059, and let me also do it one way. Let's see, p value 1 without multiplying this, because then we'll get the value from one side. And let me print the p value 1, print, and you're getting around 0.0295. But the important aspect is this is not one tailed test, it's clearly a two tailed test. So as it is a two tailed test, you have to take the value of this, because the significance level that we'll be taking is two tailed only, it's 0.05. so here also we should not consider one tailed value, which is 0.029. But when you take a 0.029, it makes sense. We think it's a it's a significant. But as per our hypothesis, we have to go for the two tailed test. Whether there is a relation, there is no relation. That's it. There ends the matter. So that's the reason I'm removing this one. I don't want a one tail test. I'm removing this completely. Okay. So what's next? Our probability value is ready. Now it's time to wrap this up. That's by comparing the p value with the significance level. So what we are going to do here is the obtained p value is compared to the predetermined significance value, a significance level, usually 0.05. If the p value is less than the significance level, the null hypothesis is rejected, indicating that the year's experience feature is statistically significant. But let's see what is going to happen here. So back to work, and the most important task had to be done. So yeah, comparing p value with significance level. Comparing p value with significance level. So let's do that. So let's take a significance level is equal to 0.05, and let's write a loop. If let's write a conditional statement. If p value is less than significance level, if it is less than significance level, it's fantastic. What we have to say is, let's reject the null hypothesis. What does that mean? What does that mean? That means the ears experience feature, just a minute, feature is statistically significant, is statistically significant. And on other side, else let's print if p value is greater than significance level, we will be failed to reject null hypothesis, and the ear experience feature is not statistically significant. Let's execute and see what statistical significance test is going to say. Okay, there is an, oh, got it. So I should have done, yeah, this mistake should not be done, but however, let me just copy this here. Yeah, sometimes it happens. We got excited with some other things, and yeah. Okay, still failed to reject. Where is the issue? Unterminated string literal. Yep, it's been okay. Here the same. That's okay. Fine. Yep. Okay. So the result of our z-test with respect to this data is failed to reject the null hypothesis. The ear experience feature is not statistically significant. That means we can't take this as a feature to the salary. Okay, but let's try to explore more, because what data is saying is, what our statistical significance test saying is, it's not significant. It's not these are the relation between them is statistically not significant. Okay, that's what it's saying. Okay, so let's try to plot, and let's try to understand more, because when you find a statistically insignificance relation, it's better to explore more. Normally that's what a statistician do. So as a data scientist, we should also follow the same. So let's plot the outputs. Okay, to plot the outputs, we have to import a matplotlib. From matplotlib.pyplot as plt. Yeah, let's plot the relation. So plt dot scatter, and inside capital X comma Y, and color I'm gonna go for the black. Color is equal to black. Then plt dot X label, and I'm gonna go for X label is our ears experience, and plt dot y label is salary, and finally let's put the title, plt dot title, which is a scatter plot of salary and years experience, and final plt dot show. and execute it. Uh, Invalid syntax. Okay. Oh, sorry, that's my mistake. Yep, that's it. Done. Okay, but when you see the scatter plot of the respective data, salary as Y and years of experience as X, it clearly, the scatter plot says there is a clear cut relation, there is a strong relation between them. Okay, but the issue is this coefficient, whatever the coefficient that we got, with that coefficient we are saying uh, the relation is not statistically significant. Okay, that's what the outcome of this demonstration. So using z-test, after doing the z-test, what we found is the relationship between them with respect to this coefficient is not statistically significant, because the data that we have used is just 30 samples. That could be one reason, and uh, the enough data is not there, and there could be many other reasons. Okay, so this is what the statistical significance test with respect to the z score, or with respect to the z statistic.